Hello, welcome to the sixth lecture in ML series. In this lecture, we will be discussing our first machine learning algorithm called FindS, which takes a data set of positive and negative examples as input and finds the best hypothesis that satisfies all the positive examples in the data set. Okay, so let us quickly recap what we discussed in the last class. We have defined a concept learning as the task of inferring a general rule or a definition from a set of labeled examples. Here we have defined as learning a Boolean functions from a given positive and negative examples, and how a target function or a hypothesis is represented is a conjunction of constraints on attributes. And we had considered an example of enjoying a water sport, whether a friend enjoys a water sport or not is a Boolean valued function that is expected to be learned, which depends on 5 features, which depends on 6 features: sky condition, air temperature, humidity, wind speed, water condition, and forecast. So an example hypothesis here is a sky condition is sunny, and that is conjunction and air temperature is warm, and humidity can be any value. The question mark is used for representing any value, and wind speed is any value, and water condition is any value, and the status of forecast is any value. This is one hypothesis, and we have also found that there are 972 possible hypotheses. Depending on the possible values those attributes takes, and we converted this problem of learning this concept or finding a hypothesis as searching in those 972 hypotheses which satisfy the given training examples. The question is, do we need to search all hypotheses, all 972? No. So that's where we are going to use the properties of a lattice by defining a partial order relationship on those set of hypotheses, and we define ordering called a general to specific ordering. Okay, so first, what is this what is this more general than or equal to relationship between the hypothesis? So when we say that H1 is more general than or equal to H2, if H1 covers all examples that H2 covers and possibly more, then we will say that H1 is more general than or equal to H2. Okay, so let us try to understand this with an example. So in the left side we have the example space. So let us consider an example x1. Here x1 is saying that the sky condition is sunny, and the air temperature is warm, humidity is high, and wind speed is strong, and water condition is cool, and forecast is same. And another example, that is x2, which is same as x1, except that the wind speed is light and the water condition is warm. Now if we consider a hypothesis H1, the hypothesis H1 is saying that the sky's condition should be sunny and the wind speed is strong. Remaining features or remaining attributes take any value. Now we can see that H1 condition is covered by X1. That means X1 satisfies H1 condition, because it also has a sky condition is sunny and wind speed is strong. But x2 is not covered by h1 condition, because as per h1 the sky is sunny and the wind speed must be strong, but in x2 the wind speed is light. Similarly, if we consider H3 hypothesis, this is a condition saying that sky condition should be sunny and water condition should be warm. Remaining attributes can take any value. This is satisfied by x1. So H3 covers x1 example. Because there also we have sky condition is sunny and water is cool, but H3 does not cover x2, because in x2 the water condition is warm. The condition is warm. So let us consider hypothesis H2. In hypothesis H2, the condition is the sky condition is sunny, and remaining attributes can take any value. Both x1 and x2 the sky condition is sunny, so H2 covers both examples x1 and x2. And we can easily see here the hypothesis H2 covers all the examples that are covered by x1, and H2 covers all the examples covered by H3, and we can say that H2 is more general than H1, H2 is more general than H3. Now what about the relationship between H1 and H3? By looking at an attribute wind speed, we can say that H3 is more general than H1, because H1 is having a condition wind speed is strong only, but H3 can take any wind speed value. But by looking at attribute water condition, H1 is more general than H3. So by combining all attributes, H1 and H3 are not comparable. Okay, and when you, so now H1, so there is an edge from H2 to H1 and H3, and by drawing these edges we can define a general to specific ordering between hypotheses, and at the bottom we will be having, at the bottom of this we will be having all question mark, that is the most general hypothesis which covers all the training examples, and at the top we will be having all 5, that is the most specific hypothesis which covers no example, and this forms a lattice, and the properties of the lattice we will be using in the find S algorithm. Let us understand this find S algorithm. So find S algorithm, the key idea is it starts with the most specific hypothesis, that is all 5, and it processes only positive examples, and for every positive example it checks whether a hypothesis covers that example or not. If it does not, it modifies the hypothesis by replacing with a least general hypothesis that covers that example. Least general in a sense that if you have a 5, it replaces with a specific attribute value. If you already have a specific attribute value which is not covering the example, then it replaces with any value that is question mark. That's the basic idea. And negative examples are skipped. That's what here. Now let us try to understand this on an example that we had seen in the last class, where we had a data set has 4 examples and 3 positive examples are there. Okay, so let us try to understand the step by step. So initially you have a hypothesis with all 5s, and after reading a first training example x1, so as we know that when a hypothesis having a 5, it says no, that means x1 example is not covered by h0, because h0 is representing no example. Okay, so h0 is not covered by x1. To cover x1 example, now h0 has to be modified and it has to be replaced with the least general hypothesis, so that x1 is covered. That means at least the sky should be sunny and the air temperature should be warm and humidity should be normal and wind sheet should be strong and water condition must be warm and the forecast should be same, so that x1 example is covered. So we will have a hypothesis h1. Now hypothesis h1 covers x1 example. Now consider a second example x2. Now hypothesis h1 does not cover x2. Reason is the wind speed is high here. Here wind speed is high. By considering x1 and x2 examples, you can see that x1 is saying that when a wind speed is normal, he enjoys a water sport. From x2, wind speed is high, also he enjoys a water sport. That means for a wind speed of any value, he enjoys a water sport. So to represent that with a hypothesis, we have a question mark. That is, in H2 we have for a wind speed taking any value, and for example x3, which is a negative example, which is skipped. So we'll get the same hypothesis for H3. Now consider a training example x4 as a positive example. Now the hypothesis H3 does not cover x4. Reason is here the water condition is cool and the forecast is changed, whereas the hypothesis is expecting the water condition should be warm and water condition same. That means x4, as per x4, even the water condition is cool and forecast is changed also, he enjoys a water sport. That can be represented in a hypothesis by having a question mark here. So we get a hypothesis sunny, warm, question mark, strong, question mark, question mark. Okay. So this is the most specific hypothesis. In a sense, at a lattice you start at the top, and you will be reaching to a point where all the points below that also satisfies these training examples, and out of those we are finding the most specific. That's why we are calling it as the most specific hypothesis. Okay, and all the steps are shown here. You can check it once. And one of the limitations of this find as algorithm is it ignores the negative examples, and as it ignores, it may find to a over generalization, which may classify some negative examples as positive, and it finds only one hypothesis. There might be many hypotheses which satisfy the training examples, and the example that we found may not be working well on the new examples, and we will discuss more issues in the next class.